Hello, everyone, and welcome. Very glad to have you all here. I'm Gabriel Musat. I'm a senior software engineer at Datadog, and I'm going to be talking today about running DataFusion on GPUs. So the first thing that I want to talk about is the motivation. Why will we want to run DataFusion on GPUs? And typically, this is the moment where I will have like 3 bullet points with all the benefits and all of that, but I'm just going to mention one thing: money. Let's elaborate on this. Let's see why exactly. Let's try to think about a very normal setup about a DataFusion deployment, which is that there's a user that is looking at a screen, it's waiting for a dashboard to render, and in order for us to provide information for that dashboard, we need to do some compute using DataFusion on the backend. Now, the requirement is this user needs to be able to see something there in 5 seconds. We need to achieve that. We might be able to achieve that with a small server, with a small machine serving one query, and that's fine. At some point, the data might be too big and it's slow. It's no longer just 5 seconds, so we might throw more hardware to the problem. We might say, okay, let's put more CPUs to this machine. Let's scale up vertically. And this is fine. This probably will work, and this will probably speed up the query, and the user will be happy. But it might happen that either the queries are more complex or there's more data to pull in. So we need to throw even more hardware to the problem, which is using distributed execution and employing multiple servers in driving forward one query. Now, the pattern here is that we are paying more for serving this query. All of the scale up and all of these CPUs that we're employing in serving one query, it's something that we are paying. So how about instead of using more hardware, we use different hardware. And instead we use a GPU to perform the heavy lifting of the compute operations that make the query slow on the first place. And this actually works. And we made it work, and I'm going to not dive too much into the details because they are a bit complex, but I'm going to explain you in a high level how it works. And everything evolves around this NVIDIA project, QDF. This is kind of like a data frame-like library for Python that allows performing data frame operations on the GPU. So this is currently used as a drop-in replacement, for example, for pandas or polars that has this like nice Python API for data scientists to do their own thing. There's also a Spark accelerator based on QDF. And the performance that they're reporting is pretty good because they are pretty much using their own specialized hardware for doing compute-heavy operations. Now, one of the things that happens with this library is that as pretty much half of the libraries that exist in the Python world, it's a C++ backbone with a pretty Python wrapper. So this C++ backbone is what are of interest to us. So we have the GPU. We have this C++ backbone, which is a collection of compute kernels written in the CUDA language. It's also a collection of tools for managing memory at a very low level in the graphics card. And it exposes the very primitives and fundamentals normally for the Python wrapper to actually do its work and implement this like nice data frame-like API. And in the same way that Python does it in the original library, we can hook into this low-level library, low-level C++ library from QDF and create some bindings in Rust. So essentially, we are just like doing exactly the same thing. We're calling all the functions and methods for managing memory on the GPU, but through Rust. And you can think of pretty much a one-on-one mapping just for being capable of using this from Rust. And this is because DataFusion is written in Rust. So we need Rust code for this. And with this, what we accomplish is that DataFusion, with its extension traits, allow us to implement custom physical plans that allow us to use these Rust bindings to lift QDF for interacting with the graphics card, launching compute kernels, managing memory, and all of this. This is an example of how a plan looks like. Hopefully, it's not too small. This is an example of how a plan looks like at the top, CPU, vanilla DataFusion, and at the bottom, the variant in the GPU world. So I'm just going to mention briefly a couple of important differences. You will see that at the bottom, there's a couple of nodes that are the first node at the top and the second node from the bottom, which is QDF unload and QDF load. And these are nodes that there's no counterpart in the CPU world because they are in charge of loading data from the CPU into the GPU and unloading the data from the GPU back into the CPU. And this is very critical and very tricky to get it right because the memory management details about moving data from CPU to GPU are crazily complicated. So getting this right is very important and also very crucial for getting good performance. And the other thing that I'm going to mention is that you will see that at the top plan, we have some partitioning. We have we see that we're using 4 partitions. We see that we have a red partition in the middle and this like partial math plus final aggregate. And this is because we happen to have 4 CPUs in a machine that is running this, but at the bottom, you see no repartition or anything like that. This is because we just have 1 GPU on the machine running this query. And if we had multiple GPUs, we probably could be also using some repartitioning, but it's worth it to get just 1 stream with very big batches in order to perform very heavily parallelized operations over these arrays and data that we get. Now, does it work? In order to measure this, what we did is that we benchmarked the same query, TPCH query 1 specifically, with a machine, an AWS machine that has 16 CPUs and 64 gigabytes of RAM. And we compare that to a different machine that has the same CPUs, but these are only 4, and has a graphics card, one Tesla 4 from NVIDIA. You see that the price, actually, the GPU part, because of having less RAM and less CPUs, is a bit cheaper. And these are the results of running TPCH query 1. You will see that even with the lack of CPUs, the one that has the GPU was slightly faster. And this is actually the repository is open source. Anyone that is willing to pay the AWS bill can just run this themselves. And the query is actually kind of nice for testing performance because it has a bit of everything. It has some filtering, it has some orders, it has some groupings, it has some expression evaluation. So it was a bit tricky to get all of these components in place, but that's what we were aiming for. And if we do some math, you will see that we are paying less price for getting a bit less latency. So doing some math with the amount of time that we have managed to spend on this effort, which is just a couple of hackathons, it's actually cheaper. It's actually 1.75 times cheaper, which for the amount of time that we have invested in this, I will say it's pretty good numbers. Now, some of the learnings that we have along the way is that, first, transferring memory from the CPU to the GPU, it's critical and very hard to get it right. Second is that it requires rewriting pretty much the full physical layer of DataFusion. All the aggregations, all the nodes that are in charge of sort, we needed to rewrite everything. And this is expected. DataFusion does not have a pluggable compute backend like, for example, some machine learning frameworks. And this is expected because it doesn't have the requirement to adhere to multiple architectures like it happens for machine learning frameworks. So that was expected. And also the mental model about thinking about parallelism and compute is just vastly different. All the assumptions that are valid on the CPU world are no longer valid on the GPU world. So it does require a shift of mentality and assumptions. And this is it. Happy to take any questions. Okay, so the question is there any kind of queries that benefit most from GPU execution versus CPU? The answer is yes. It depends mainly on the ratio of compute versus I/O that is happening within the query. So if your query is very I/O bounded, it doesn't make sense to use GPUs because you are paying the price of transferring data to the GPU and not really benefiting from that. However, there's different queries that, for example, the kind of queries that you will use in benchmarks are very good examples because they are designed to stress the processor of the system. So yes, it's mostly CPU-bounded queries. Any CPU-bounded queries is a good one for getting sped ups. You mean, so the question is whether there's some specific floating point operations that are cheaper to execute on the CPU versus on the GPU. I think any kind of operation that is strictly sequential, that you rely on the item before to have been computed in order to compute the next one, that's going to be for sure worst on the GPU. There's algorithms depending on the thing that you're trying to do that kind of reduce the complexity of all of this, but yeah, it depends on the kind of operation rather than the data type itself. I will say typically in the same way that you can assume that it's safe to use all the CPUs in vanilla DataFusion, if you have multiple GPUs for driving a query forward, I can see how you could probably just like use them all. And to be honest, we didn't go that far. But yeah, I can imagine how you will tend to prefer to use as much as possible if there's not overhead in doing so. Adrian?
What parts of the execution plan are running on the GPU and what parts are running on the CPU? Is it like you ported like a scan decode filter to the GPU only, or is the group by and the arbitrary expression evaluation, like is that all also running on the GPU?
So that depends on how much effort are you willing to put to rewrite the DataFusion physical plans. So there was a time where, for example, we were not able to perform aggregations and we were still able to run TPCH query 1. But there was a QDF unload before the aggregation and a QDF load again after the aggregation. Of course, that was terrible for performance. But you can technically do so. Ideally, you should not do that. You should keep everything onto the GPU because by far the bottleneck is the network, sorry, the data transfers between the CPU and the GPU.
Feel like you were working with DataFusion or fighting it? Like did DataFusion make it easy to say, run this on GPU, run this on CPU, or was it,
To be honest, it makes it very easy because we are able to reuse the full parser, logical planner, physical planner optimization rules. We were able to reuse everything. It was not easy to implement it at the physical level because we essentially need to rewrite the physical layer. And I will not say that's DataFusion that is making it hard. It's just how things are. Mm-hmm. Right now, we just rely on the optimization rules that vanilla DataFusion decides, and we just follow what it suggests on the CPU. So, for example, if it decides that there's a join and this part should be at the left of the join and this other part should be at the right, then we just do so. We do not apply further logic. I can imagine how GPU execution could change that, but we, for now, just follow what DataFusion has to say. Yes, all the wiring, it's up to you. There's extension points that DataFusion exposes for you to do pretty much whatever you want at the either logical level or physical level. The thing is that you probably will need to implement that yourself. I mean, you can do that, but it's more your code. Like there's traits, there's arbitrary code that you can put in those traits. And if you want to follow a cost model for, I don't know, rearranging how the plan looks like, you're free to do so, but you need to do it. I think we might be already good for questions, right? Happy to take any more follow-up questions. Sorry about that. Happy to take many more questions after we finish the talks, and we'll follow with distributed data fusion.